Alrighty, looks like we're live. Hello everybody, welcome to another stream on the Pico W balancing robot. So last time, so this is the third stream on the balancing robot, and the last time we got, we got free RTOS networking working. We were able to send a string over UDP to a Python script running on my desktop. We were able to get the MPU6050 working, and it was sent. We were able to get MPU6050 going. It was reading data from the DMP on the IMU, which is reading the orientation from the MPU's motion processor and sending that over the network to, again, our development desktop. And we were, let's see, what else? What else did we get done? And I think that's major, let's see, I think we did something else. I think that was majorly it on what we did. So, however, at the end of the last stream, we had an issue where essentially after just a short amount of time, the IMU would freeze. It would stop getting data completely. And let's see. So the way that we are currently the way that we're currently accessing data from the IMU is we're basically just mirroring the example that was given in I2C devlib. Basically, it just slams the IMU with polling requests. It just sits in a loop checking what's the FIFO length. If there's enough data in the FIFO to read a whole packet out of it, there must be a packet, so it reads. But essentially, this means that we're always on the wire and we're always slamming the IMU for data. So maybe that could potentially be a reason that the IMU freezes. Looking into some things off stream, another interesting thing was that the address 0 pin on the IMU board itself isn't always tied to, or I don't believe goes through a pull-up resistor. So we need to tie that directly to ground in order to ensure that the address doesn't change, but adding that didn't help. Same crashing issue. I also tried slowing down the I2C clock, and that also... So I tried slowing down the I2C clock, and that seemed to help quite a bit, but it didn't fix the problem. You know, rather than crashing after 10 seconds, it would crash after a minute or so. So today what we're going to try to do is migrate from this polling approach to an interrupt-driven approach for basically only asking the IMU for data when there is data available, rather than, or when the IMU says it has data available, rather than just constantly slamming it trying to check for data. So while we're waiting on maybe a few more people to trickle in here, what we're going to start with doing a little bit of cleanup. I'm going to get this posted on GitHub so that you guys can follow along. So we're pretty much like I've been copy and pasting some stuff in here from other projects. So we're just gonna make notes of what we used. So the first thing we're gonna do here is just turn this into a Git repository. And actually, you know what? I didn't do this on previous streams, but I think what I should do probably is, okay, here, hold on. Maybe make it a little easier to read. So we're then going to, let's see, what all do we got? We're going to add, let's see, what's in our git ignore? Just build, and we're going to put the virtual environment in the git ignore, and then I think that's pretty much all we need. Well, okay, also, just so y'all don't steal my Wi-Fi password, we're going to stick the cmake kits.json also in our git ignore. And then, so git status, and then we are going to, I think in Pico SDK, actually, sorry. So, all right, so we're going to add, okay. All right, so First thing I'm going to do is I'm going to add the free RTOS kernel as a submodule in here, just so we can stop having to worry about this environment variable. So we're going to make ourselves a dependencies directory. We're going to do a git submodule add. I probably added free RTOS for some other project in here. HTTPS github.com. I believe it's free RTOS / free RTOS kernel. We're going to call that free RTOS kernel. All right. That's adding our submodule. And then we're also going to move the I2C devlib code from earlier into here. So actually, sorry, we're going to first start by I2C devlib, copy that to here. I want to just make sure that I'm following any sort of licenses correctly. So I am going to just check the, so this is our I2C devlib library that we used in the last time. I am just going to copy the license, which, let's see, what license is it under? Oh, I thought I saw a license, or is there README installation? Did they not put a license on this? That is funny. MPU6050. No, they did not. README does not like they does not. Okay, come on. This has to be easy enough, right? Contribute. What is the, if you don't want to use GitHub, what is the license? Do they say? Maybe it's in some of this code here that they've posted. Based on update should, MIT license. Okay, cool. It's just the MIT license. So we're going to add a README in our vim readme I2C, oops, I2C devlib. This code is lifted from I2C devlib. And with modifications, those are I2C devlib. Modifications were made to upstream. Modifications were made. This code is lifted from I2C devlib. The I2C dev class is modified to support. We're going to actually try to support DMA here eventually. So we're going to do DMA. And the license is MIT. And it is MIT. I'm going to do MIT license. Jeff Roberg. Okay, cool. And then what we're going to do is copy the unmodified ones from the source directory to, let's see, where did we get this from? Sorry, I2C devlib. There we go. RP2040, I2C dev star devlib, RP2040, MPU6050, H2 dot star dot CPP2 dot star dot HPP dot. Examples DMP, and that's just our stuff. All right, cool. So we're going to git add dot, and then we're git log, sorry, git status. Then as this is the first thing, we're going to add git ignore and git commit -m, add the legally chicken fingers. Okay, git commit add the I2C dev lib code for RP2040, and then we're going to add then status git add one concurrent viewer. All right. Let's see, git add ... What else is in here? Copy ITC dev lib star to basically all I was trying to do here was get the unmodified stuff from upstream checked in so that our modifications are visible on top of it. So sorry, devlib into devlib, and we can do a git diff dot. Or not. Get status. Or not, I guess. Oh, did I just copy? What did I copy in here? ITC dev. Did I? Oh, right. I modified upstream. Okay. Oh, well, whatever. So, never mind. We shall copy... so we're going to add a, sorry, I'll just double check this, star to dependencies, ITC devlib. All right, and get diff dependencies. Cool. All right, and we're going to add a CMake list in here, new file, or sorry, before we do that, git submodule update init recursive dot. All right, because we want to get all of the community supported port stuff in free RTOS. So now we can go into here. We can make a CMake lists file to pull in our dependencies. CMake lists, CMake minimum required version 3.13. We're going to add subdirectory. We're just going to go into this. What was the kernel import? We're going to add, let's see here. If Pico platform, we're going to copy this. CMake lists. If, all right. So I didn't do that. If Pico platform, perfect. So what that means is that we do a git add subdirectory portable third party relative. Oh wait, hold on. Is that already? That's already in here, right? Pico platform. Oh dear. Wow. Hold on. Sorry. Brain fart. All right. So, if let's see. Add correct free RTOS kernel for our platform. Add the correct. All right. So we're going to do add subdirectory, CMake current lister. We're going to go free RTOS kernel / portable / GCC. I believe, actually, no, sorry. It is / comment, no. Wow. Third party GCC RP2040. Yes. All right. free RTOS kernel, portable. Third party. GCC RP2040. All right. And then if we pull that. All right. And then if we are I call it a RP2350 or the Pico 2, it is actually in partner supported ports, GCC. No, wait, nope. It is in, sorry, third party community supported ports, GCC. That, okay, so it will be in third party community, community supported ports / GCC, and this will be RP2350 RISC-V, and that would be RP2350 ARM NTZ. All right, and all right, cool. We do that. Oops, and then add I2C dev lib source. Add a library for add I2C dev lib sources. Add subdirectory. CMake current list dir / I2C dev lib. I don't have to do that part, right? No, sorry. I don't think so. I can do a relative path. I do I2C dev lib. Cool. All right, cool. For RTOS kernel, I2C dev lib, new file, CMake lists. Minimum required version 3. Add library. See devlib static. We're gonna do I2C dev CPP. MPU6050.cpp. All right. Add, target, include directories, I2C dev lib, public, build, interface, make current list dir. All right, and then target, link libraries, I2C dev lib, public, and this, or actually, I mean, technically, because it's static, private, Pico, I2C, or that's not right, is it? I think it is, CMake list, we did, Pico, oh, it's just called hardware I2C, okay. Cool. All right. I think. All right. Cool. And then in CMake list up top, rather than linking all of this crap, what we'll do. Actually, we're going to nuke our build directory because this is going to change a lot of things. We're going to remove the free RTOS kernel import. What we're going to do now is pull in dependencies, all right, include project, SDK initialize, all right, add subdirectory, dependencies, all right, remove that logic. We're going to remove that bit. We are then going to, rather than linking to hardware I2C, we're going to link to I2C devlib. And maybe we can build. Pico standard lib. Okay, so we need to add Pico std lib. And it's actually and then Pico balancer fails because what? Hardware I2C, no such directory. All right. That means we need to link to hardware I2C still. All right. Private redoot hardware I2C. Because we are talking to hardware I2C, so we should link to it. All right, perfect. We are building. Awesome. And I2C devlib, free RTOS. Perfect. Perfect. All right, we are now no longer using this free RTOS kernel import statement, or kernel include thing. All right, so now we'll do one. So now we can delete this, and then we can add new folder. We'll just add a source folder. We're going to move our Pico balancer program in there along with our little headers. Move. All right. Create a new file. CMake lists.txt. We're going to do a CMake minimum required version 3.13. And then what we're going to do is move the, what do you call it? We're going to move our executable stuff to our source directory. So this just lets us do add subdirectory source. So add project sources. Why not sources? We'll do this, we'll do that. Just gonna move this up here just to make it easier. This is a option, so we'll actually pull this back into the top level. Add configuration options for the SSID and password. All right. Sources, Pico balancer, sorry. For our top this, we need to add our current directory. And that's technically part of our build interface. Build interface. Pull those over. All right. To just target compile definitions. All right, perfect. And I believe that will do this. Will do us. All right, perfect. Okay, sweet. And status, git add dot. Okay, git reset tools dot checkpoints. Sorry. Just gonna, until I figure out more about the Jupyter notebooks, we're just not gonna worry about including them for now. All of this stuff, cool. SDK import, awesome. So we'll just amend the previous commit since I didn't actually do what I needed to do. We'll just call this first commit for first commit. Sure. That's a horrible thing. All right. Vim readme.md. Why am I vimming in there? Sorry. New file readme md. Pico balancer. Let's see, a balancing robot built around the Pico W and the MPU6050. All right. Get add readme. Sorry, just one more commit amend. First commit status at the end of the. Sorry, status at the beginning of the third stream. Perfect. All right, and then we'll add. I already set up a Git repository, so we're just going to do our add a remote, then push origin main. Perfect. And then there is now a Git repository. I'll post a link in chat. I'll add it to the description later. But if anybody would like to follow along, how much compute is required for the balancing calculations? Honestly, it's not that bad. The MPU the IMU outputs, I believe, about 130 something orientation estimates per second. So 133-ish times, let's just say 20 or 30 floating point operations. Like it's only a couple of, maybe a few thousand floating point operations per second, which is a fraction of the compute power available on the Pico. Not much. The short answer is not much. The long answer is that it probably would take 1 to 2% of the CPU cycles, at most. All right. So post the link in chat. This is the Git repository. Repository will be working out of. And you know what? Let me add a little build instructions. Build instructions. Git clone recurse submodules. Open with the. Actually, sorry, what am I doing? Open with the Pico Visual Studio Code extension for it. All right. Perfect. And we'll just add that readme git commit git commit add build instructions. Perfect. Right, now we have some build instructions. Cool. Very good. Clone recursive modules. Perfect. All right. Now, one thing that I did want to, I'm just checking because I bookmarked it on my phone. I wanted to try and add, so one of the things that we were looking at was in our launch. Remember, if you remember when we launched the debugging mode in the last stream, we would basically freeze right before main. There is a there's a statement here, run entry point. So if we delete this, or actually if we delete that, change it to something else. So I think it's a stop on entry, false, or maybe property is not allowed. Okay, never mind. We're just going to comment out this run to entry point, and maybe we will not freeze when we start. So I'm going to plug the batteries into the robot, And we're going to try to launch the debugger again. All right, I've got that one in, and then this one. And there's no polarity protection on the robot, so better get it right. There we go. All right. So, let us. Okay, so if we build this, and then let's try to launch the debugger. Pico debug, Cortex debug. Presumably, it will not freeze on launch anymore. Presumably. There's 2 watch points. External reset detected. Presumably, it's just doing whatever it's supposed to be doing. And if we were to say pause, oh no, it's doing something. Pause. Ah, perfect. Idle task. The other one is doing I2C read blocking. Cool. Yeah, that worked as expected. It did not freeze when we started the debugger, which is nice, because that was causing all sorts of fun issues. Because we were trying to catch what happens when the MPU freezes, and I was noticing that there was a bunch of problems if it started up and then immediately froze. But so we'll kill that, and then what we will do is, now that we have this, go into our tools directory, and we'll start the UDP receiver. We will then start the debugger and hopefully see the same status as before. We did change some things, obviously. So let's see if we have data come in from our MPU. You should. It'd be bad if we didn't. So we're running, and presumably we'll start seeing stuff come over. Maybe. Maybe. Hey, okay, cool. So we're seeing stuff come over from the MPU. And then, cool. Okay, so since we're seeing this, which is nice, this is actually running a lot longer than it used to. Did I leave that slowed down version of the thing? Sorry, did I leave the... Oh, yeah, sorry. I left it set to 100 kilobits per second on the I2C, and notice it's a lot more stable than it was before. And all right, we're now a bit into this. All right, so one last piece of cleanup. And again, looking at my phone because I bookmarked it on my phone. Now I can finally close this tab that's been open for 3 days. All right. What I would like to... So, let's see. There is an option. Oh no, I've lost my spot. Well, I guess I have to Google again. All right. Oh, see, it did freeze. All right. It's possible to enter. There's this RTOS tab that you can see. So it is possible to tell OpenOCD to assume that what RTOS you're using if it's one of the standard ones. So like FreeRTOS or ChibiOS or NutX if you're using the extended OpenOCD. But OCD. On circuit debugger, not obsessive compulsive disorder. Sorry, we can tell OpenOCD that we're using an RTOS, and it should give us a nice like thread view rather than just this core view, supposedly. So OpenOCD, FreeRTOS. I think it's just pass. We might just be able to tell it in our launch settings in OpenOCD commands. Maybe. Config files. RTOS auto. Monitor. Okay, target. OpenOCD. Maybe there's OpenOCD launch commands, override launch commands. Maybe there is a -F. Maybe oh, perfect. FreeRTOS. Okay, cool. There's already an option for it. That is nice. Let's try running it. See if that does what we expect. Shouldn't change the code. Cool. And if we run Pico debug, maybe we get oh, I have to capitalize it. Okay. The fully qualified name. All right. So Pico debug. Maybe we're running. We're running. Okay, XRTOS. RTOS, some sessions are busy. No RTOS. RTOS detection may still be in progress. Oh, hey, maybe if we pause, RTOS detection will work. No. Well, we tried. All right. I'll try that again in the future at some point, which is fine. So, timeout check. ITC right blocking internal timeout. All right. All right, so let's just kill all this stuff that we're not using. Perfect. Okay. So, well, all right, so we'll just kill that tab. Sorry. All right, that's all the cleanup bookmarks that I had. All right, so we added FreeRTOS as a submodule. We added the code for the I2C devlib. We moved our code into a source folder. We uploaded it to GitHub. All right, awesome. So now let's actually get into what we're going to be working on today. So the first thing, welcome anybody who's currently viewing. Thank you for watching. So the first thing that we're going to do is we are going to switch to interrupt-driven mode on the MPU6050. So I have a pin. I have a GPIO 9 on my Pico W attached to the interrupt pin on the MPU6050. And what I'm going to... and then in theory... the DMP interrupt is already enabled. You can't really change the configuration options because there's this just binary blob that came from some InvenSense sample at some point that nobody actually knows internally what it does. But it does say down here, there was a comment, interrupt enable raw DMP interrupt enable is on. So presumably... maybe we get interrupts when the DMP kicks. So, yeah. So, yeah, it says no interrupts, base interrupts, and then DMP interrupts on. So, first thing that we need to do is create a bridge between a free RTOS, between one of the PyPico's interrupts and free RTOS, a free RTOS task. So... what we're going to do, or the idea anyway, is we are going to start with, there is a function in the Pico SDK called a GPIO add raw handler. And what it does is it, oh, wow, it didn't zoom in. GPIO add raw add IRQ handler raw? No, add raw IRQ handler. Oh, sorry. Add raw IRQ handler. All right. So what this should do is essentially, wow, I'm blanking again. Sorry. This should, so unlike what we would do on like an Arduino, where some pins have dedicated interrupt lines, and you would add a handler to handle that specific interrupt. On the PyPico, the RP2040, there is only a single GPIO event interrupt, essentially. And the system, or many things in the system are automatically subscribed to this interrupt. So in one of the later Pico SDKs, they added this function, basically GPIO add raw handler, which what it will do is basically automatically builds a chain of handlers. And so the contents of your interrupt handler basically needs to be, if the GPIO that I'm listening to is the one that provided this event, acknowledge that GPIO's interrupt. So that's what this bit in here is my handler. If my GPIO, the pin we're interested in, is what set off the interrupt, then acknowledge the interrupt, and then do whatever it is that you wanted to do. So let's actually just start by writing this handler task. So we're going to call this the IMU IRQ handler, and it doesn't have any parameters. And then what we're going to do is, getting ahead of myself here. The interrupts on these devices typically are either falling or rising edge of something. So, or when you are trying to notify the microcontroller, usually this event is signified by a pin going high or a pin going low, or maybe it being high is the interrupt or the interruptible condition. So we call it either edge triggered or level triggered. Edge triggered is if the line goes from low to high or the line goes from high to low, that there's an edge, then trigger an interrupt. And sometimes it's what's called level triggered, which is the pin either being high or being low is what is triggered. And then once you clear the event, the line will then come back down. So I don't actually know on the interrupt pin for the MPU6050 if it is what the interrupt condition is. Is it I don't know if it's a rising or falling, so we're going to look on the internet and see if anybody else has looked at this. So DMP data ready. True. Oh, this is the. So this is not an interrupt driven version. Sorry. This code doesn't. DMP ready. Sure. Refresh. No, we just want touch. Maybe it is the J Remington I'm just trying to figure out whether the DMP is rising or falling edge. Enable the. Oh wow. So we're just gonna click around and we're looking. Are we looking for rising or falling edge? We're just presumably rising edge. So, according to other random stuff on the internet. All right, we're gonna try that. So, we go back to our acknowledge. All right, so if GPIO get IRQ event mask int pin anded to my event mask, which shall be rising. RQ edge rise. All right, perfect. And then we shall GPIO acknowledge IRQ int pin and GPIO IRQ edge rise. Perfect. And then to do interrupt condition. All right. So, so now we need a way of notifying the RTOS that this has happened. Or, well, actually, before we even get to that, let's schedule this IRQ. So, back down and deep down in here, we're gonna do. Actually, deep down in here, or actually, wow, I keep saying that. So over here, beginning of the IMU tip, we're going to initialize the IMU. Now we're going to subscribe to IMU interrupt. So now we're going to do GPIO add raw IRQ handler, int pin, and IMU IRQ handler. Perfect. All right. So, although I'm kind of scared that this might run at the same time as the other one. So, I'll actually just... Oh, well, whatever. If it breaks, it breaks. All right. So, we now need to notify the RTOS that the interrupt condition has been triggered. So what we are going to do is use what is called a semaphore, or a binary semaphore. Basically, we're going to use it as a a flag to wait on, essentially. So we go back over to a free RTOS documentation. We're going to look at direct task notifications. Potentially, we've got task notifications. We also have semaphores and mutexes. So we can create a... Actually, an easy way of doing this, just so we don't have to modify any of this code here, what we can do is we'll actually do a counting semaphore, and then use that to we'll do a counting semaphore, and we will, let's do a static counting semaphore. All right, include, it's in, is it semaphore dot, yeah, it might be in semaphore. Yes, all right, cool. So we're going to do, we're going to give ourselves a static semaphore T, like semaphore handle. Okay. That's unfortunate. Okay. We're going to do, actually, so we'll just do semaphore handle T, IMU semaphore, IMU semaphore, IMU sem, and then we shall do this, IMU sem, max count, when this region no longer be given, maximum count, new base type. So what we'll do here is we're going to make sure that before we add this, we're going to do IMU sem equals x semaphore create counting. We're going to assign a max count. It's just something large like 100,000, and she'll count as 0. Then we're going to x semaphore I think it's give ups the semaphore macro must not be s semaphore give fail because we can't get, okay, so take first taking it. I'm trying to think of what ups and downs. So sorry, so give, sorry, so take increases the count, right? Macro to obtain the semaphore. Semaphore is previously created a call, must not be called from an ISR, use receive from ISR, form available. Actually, sorry. So you know what we're just going to do, we're just to make this a little easier. Okay, binary. We're just gonna use a binary semaphore. We'll just use this as a mutex. Semaphore. The value can be given. X semaphore. Actually, no. We'll keep doing what we were doing before. Give ups, right? Direct to task notification. Sure. Obtain the semaphore. We have to take it first. So I think take ups the count. No. Yes. No. Let me scroll up. Macro to release semaphore. Semaphore must previously created with a call. Must not be used or create counting. So, all right. Let's just read this. Great counting. Semaphore. An event handler will give a semaphore each time an event occurs, incrementing the semaphore value, and then a handler test will take. Okay, cool. Oh, I should have just read that before. Okay, so give is what we want to do. Event handler will give. And handler, yeah, so event handler, so we're going to do give from ISR. We're going to do sample, x semaphore, ISR, x give. We're going to do x. So we're going to do base type t, x higher priority task woken equals PD false. And then we're going to do an x semaphore give from ISR, and we shall do IMUSEM, and then a pointer to x higher as well woken. We'll just put that up here because that's what it wants us to do. X semaphore give from ISR, higher priority task woken. Port yield from ISR. Okay, perfect. Port yield from ISR, X higher priority task. Okay, all right. So now what this will do is whenever this interrupt handler runs, it will then up the count of this semaphore. And then just to debug this essentially, what we're going to do, just to make sure that these are actually ticking, what we're going to do is we're actually, as part of our main task, we're going to get the value of this semaphore and add it as part of this string, the what do you call it? The message string to the server. So we're going to look at the UX semaphore get count. So we're going to say auto count equals UX semaphore get count, and IMUSEM, and then we'll just decrease this to 128, and then we're going to do count is probably an unsigned. Yeah, it's an unsigned. Okay. Compile. That built. Perfect. All right, so terminal. Restart this. We're going to start the debugger. So to anybody watching, if you ever have any questions, please just feel free to interrupt me. I'm keeping my eye on chat, so if you have any comments or questions, feel free to ask. All right, so we're given in loop, and now nothing is happening. You know what, I probably needed been a good thing to actually configure the GPIO pin. Okay, GPIO set function int pin GPIO func GPIO. Actually, sorry, I don't have to do that. We're not changing the function. GPIO set direction. Int pin false. Maybe there's a function. Int pin. Is there an interrupt control? No. We were fine on that. I mean, it should have been an interrupt. I mean, it should have been an input by default. Can we ping the balancer? Oh. Is this thing even up? Is this frozen? Well, it looks like it froze. That's not good. For acknowledge IRQ edge rise. Oh, I might have GPIO. Alright, hold on. I'm missing something. Pi, Pico, GPIO, interrupt, C, example. There's something I missed. There's some configuration that we have to do to configure it, because there's the handler, but we have to configure it as okay, cool. That's what we did wrong. I have to do a GPIO init into pin. And then we do a there's an interrupt here somewhere. Sorry. There is, oh, that's right. GPIO set IRQ enabled int pin GPIO IRQ edge rise. I think we do that before we do the callback. Just 1,000, just something. File. Oh, I did that wrong. IRQ enabled. Oh, sorry, true. Are independent per processor. This configures interrupt for the processor that calls the function. Oh, that's not good. Because that means that this will right. Independent per processor that calls the function means that because our task might migrate cores, it'll only trigger the interrupt on the core that called this. Which it's not happy about. Too few arguments. Oh, did I not save? Oh, I didn't save. Wow. Okay, cool. Perfect. It built. See example GPIO set. Oh, GPIO add raw. IRQ. Experiments. Init. Multi-core launch. IRQ enabled. Handler 1. All right. How do I probably? Okay. Well, I mean, let's see what happens. All right. Cool. And then we shall run and see what happens. See what comes up on the network. Oh, there we go. Oh. Let's now try running that again. See if it comes up. So the polling frequency of the brains, IRQ handler, what semaphores do we need to set? All right. So essentially what's happening is, so the IRQ, there, it's not polled, it's a hardware event. So when the hardware inside the GPIO controller detects that this, whatever event you asked it to listen for happens, it will trigger it. Basically, it'll trigger what's called an interrupt, which basically it tells the CPU, or it causes the CPU to jump to some piece of code. It interrupts the flow of execution, and it will jump the CPU to some predefined piece of code. The CPU will then do that and then return control back to wherever it was. So the polling frequency is just literally effectively the clock rate of the CPU. It can only do so many interrupts per second. I mean, there is a functional limit on how fast the CPU can service the interrupt based on its frequency. But for the most part, just assume several million samples per second, kind of thing. And then what we're doing with the semaphore is we're using the semaphores to... We are using a semaphore basic to keep track of how many times this interrupt handler has been called, just to verify if things are working or not. And so when we set the semaphore, it atomically increments the count. However, it is just being weird. I might have broken something. Call stack. Ooh, I only see one core. Unmute task, initialize clock source, write bits, blocking. Interesting. I don't like that. Alright, we are going to power cycle the Pico W and see if that helps. Just in case. We might have left the MPU in a bad state. Ah, yes we did. Alright, cool. And it looks like we're never triggering the count, which is sad. Oh, actually the interrupt does trigger... Our interrupt... the interrupt handler is being called that. That's what we wanted. Whether it's actually our event or not is another question, and we froze it because of that. All right, so that actually is what we want. Well, presumably. Acknowledge IRQ. All right, so our task is being registered correctly. That's a good thing. Our IRQ is never being. We never see the MPU, which is strange. We never see the MPU throwing an event. So let's try that again in a different way. Yeah, okay. Yeah, we're never seeing our MPU throwing an event. That's sussy. Okay, you know what? What we will do though is we'll pull this interrupt pin. We'll see if I can short this to 5 volts and see if we ever get an event. Yeah, hold on. Let me grab a wire. Let's just see if this detect is working at all, whether it's the MPU or just me not knowing how this works. I think this is actually just me not knowing how this works, because I am connecting this to 5 volts and disconnecting it, and I'm not seeing our interrupt being thrown, so I think that's mostly means that I'm just not doing this correctly. All right, so that makes me feel a little bit better. Okay, so that means that you know what, we'll do a GPIO in, which is 0, and then GPIO pull up into pin. And this is the pin. This is pin 9. I am reading this right. Yeah, yeah. Yeah, GPIO 9. Yeah, not completely insane yet. Okay. So what are we doing wrong? We'll just reboot that again. Except with some, nope. It did build the code. Good. Pull up. Is now running, presumably. Okay, continue. Let me. All right, I'm connecting this interrupt to ground, and okay, I have. Okay, I'm fairly confident that I have set up this interrupt wrong. Okay. So, set IRQ enabled, event mask. Events which will cause an interrupt. GPIO rise, 8. Alright. XOR mask. Okay. What am I doing? Wrong. Okay. GPIO add raw handler. No. Okay, I actually did something wrong. Okay, hold on. What we shall do, though, is we'll also, just as a sanity check, we will sample the status IO sent you. We're going to do GPIO get int pin high low. Alright, cool. Stop file run. Oh Jesus. Okay, the next session to start. Sorry, debug. Go back to our thing here. We run our receiver. So, okay, just to explain what's going on right now. We are trying to figure out why I'm not seeing any interrupts being triggered when I am changing this pin. All right, so let's see if... yeah. I mean, clearly the CPU can detect the pin changing state. You can see it flipping between these two different numbers, and that's because I cast a string pointer to an unsigned because I'm an idiot. All right, so clearly the CPU can tell that the pin is wiggling state. So the GPIO is configured correctly. The interrupt is clearly not. Otherwise, that changing state would have triggered this interrupt handler, which it's clearly not. So something about this GPIO IRQ enabled is not being done correctly. GPIO. Okay, two interrupts. So clearly I am not doing something correctly. I keep saying that, but I still don't know what I'm doing wrong. Alright, let's check another random bit of code on the internet and see what happens. So pull up IRQ enabled with callback. Handle interrupt. Handler function. Don't know if that works the way I think it does, though. Add raw IRQ handler. I mean, that worked, but we also get IRQ mask, event mask for our pin, which we did, anding it to rise, which might not even be right. IRQ event. Explicit, independent of the default event, this method default callback. Alright. GPIO, get IRQ event mask, our pin number, and it to the event mask, which is IRQ edge rising. Okay. Set function, get function, set pulled up. Maybe. It might not be. Should be inline. It's possible that we would need to do X and Y. I remember there being a sample. Here, let's try to pull the samples. There's got to be one for interrupts. Come on. Interrupt. Maybe it's in the GPIO. Where would be there's an interrupt. GPIO IRQ. 3 months ago. Well, who knows? GPIO init. Watch pin. Event string. Just remember there being a problem with the callback and free RTOS was the thing, but maybe not. Maybe this was it. Bootstrapping class, enable interrupts. Enabled. Oh well, let us just try that version. Start the scheduler. Because it was, well, I mean, we were getting into this handler. It wasn't ever throwing for our thing. Hold on. I'm curious. Hey. Okay. So input enabled. Did do GPIO set input enabled. I mean, that can't be. Can't really be what happened, can it? GPU pull up. Still not triggering. Alright, oh well, I mean, it'd help if I did that. Maybe we have to do this before. Who knows? I don't think though. Huh. Wait, what? Why? Enter boot on. Something went wrong. Alright, clearly. Not supposed to do that. Set IRQ enabled. Not enabled. It's enabling the interrupt without a callback set. Oh. Oops. If that was it, that's going to be sad. Hey, it's because I did it freaking backwards. Okay. Lovely. Okay. Okay. Just reversing. Setting the IRQ enabled without a handler installed just didn't do. Oh, jeez. Okay. Well, actually, before I trip over my own. Before I say that, before I definitively say that, we're going to move these back up into the into here and see if that makes a difference. And then if it does, we'll know. All right. see if we trip low, high, low. No, it doesn't. Okay, maybe we can't configure interrupts from inside a task. Maybe we have to do this before the scheduler starts. Okay. So we'll create that counting semaphore down here for any of this. Task. Okay. Okay. Let's see if that runs. Okay, give from ISR. Let's see if this starts coming in again. Sorry, I get a little quiet when I get frustrated. Okay. We're going to restart that, and then we're going to restart this, see what happens. I may not be able to. Oh, there we go. All right. So let's trip this. Hey, it runs. Cool. Cool. Hey, look at that. Every time I tap it, it now counts up. Perfect. Okay, now let me actually connect this interrupt pin back to the IMU and see what happens. And we see it counting up. Perfect. Okay. And it hits 1,000. That's the maximum. Okay. Okay. Awesome. Okay. Awesome. Perfect. I really should be kind and... Okay. Null pointer check is not the worst thing in the universe. Okay. Cool. So now... Awesome. Okay. Awesome. I keep saying that. Okay. All right. So what we're going to do is we're now going to, rather than this, well, actually, we can just leave the count thing there for now. Why not? What we're going to do is we're now going to take from the semaphore, wait until semaphore is lockable or has contents. Why not? Okay. So we're gonna do X semaphore take, and then that's going to be IMU sem, and block time will be port delay max delay. Perfect. Okay. And now we won't check the FIFO unless actually, sorry. FIFO while FIFO count is greater than or equal to packet size. Get FIFO count. That is a UNT. Okay, so that is a 0. I'm gonna say that is a while FIFO count equals is greater than packet size. I'm not gonna need that check. Don't need that. So basically, we'll wait for the semaphore. We'll then read as much as we can out of the FIFO as possible, and then we'll do what do for minimal changes here. All right. So take semaphore. Awesome. Okay. So now we're going to build. We're going to compile. Make sure that works. UDP receiver, run. And hope that it works. Pause. Where are we at? Vport spin lock. Perfect. Just getting impatient. Huh? I think the this launch thing broke my full debug here. All right. As we pause again, while timeout. It's doing a thing. All right. Stop. Why not? Let's run and see. Do we get stuff? Let's see. What do we get? FIFO semaphore take. No, it's not working. Okay. It was working. Where are we at now? Pause. Why are we stuck in sleep? I don't know. Why are we stuck in sleep? I don't like that. Why are we stuck in sleep? Alright, we'll just give ourselves a good old reset on the power. Interesting. You know, I wonder if creating the semaphore here actually was a bad thing. I wonder if we should create it up here. Okay. Or actually, I take that back. Q handle. Compile. Oh, yeah, that was why. Okay, cool. And maybe it'll start running. Maybe. There we go. And now we're running. And now... Interesting. I was curious right at the beginning that it did that. Let me restart that. See what that looked weird. Maybe that was just because it paused, and that's why it had to go down to 0. Interesting. I wonder why it took so long. Okay. So now we're 550. Okay, so now we essentially are waiting until some foretake. Rather than, you know, I still don't like what I was doing here. We're gonna revert this back to the way it was. One semaphore D-tick per check. Info count, packet size. It's still wrong. It's auto. We're gonna revert that. Revert that. We're gonna revert this too. Just back to the way that it was before. We're going to remove the pull up because I don't think that's necessary. And then we will, what do you call it? Yeah, sorry. We're going to remove the GPIO check from here. We'll keep count just for now, just to know how behind we're running. And then we'll do compile, stop that, do a run, refresh that. Alrighty. Takes us a while to catch up, but we are going. Perfect. All right, so now that we got that, let's just do one final check. MPU6050, rising or falling edge interrupt. Oh, okay, well we were doing this wrong. Interrupt is designed to be open drain, meaning low. Designed to be an open drain. Oh, interrupt is an open drain output. Oh, we do want to pull up then. Okay. GPIO pull up, but we actually want to do edge falling. Which means we need to change our logic up here, edge fall. We'll remove that. And edge fall. Okay, edge fall, IMU semaphore. Wow. Perfect. If IMU sem, do that. Stop, and then build. And then run. All right. Again, anybody watching, just feel free to interrupt me, ask questions, make comments. I'm trying to keep an eye on the chat. If any questions, yeah. All right, so still working. Perfect. All right, so now we have an interrupt-driven. Now we have Well, I'm tripping over this again. We now are using an interrupt-driven loop to read the FIFO off the MPU6050 rather than the polling approach. And so now what I'm going to do is I'm going to speed the I2C bus back up and see if we still see any of those crashes. Hopefully we won't. We still might, because I don't think we're actually respecting any sort of like timeouts. We're gonna change this part back to the way that it was. That goes back to 64. Let's move that. Perfect. All right. Cool. I'll just change this to script IMU interrupt. All right. So we'll stop that. Compile. We'll run. Does that init the interrupt? Check hardware set bit. Oh well, whatever. All right. Middle. All right, and we're running again. All right, and we're still interrupt driven. All right. So hopefully we won't see any crashes. So now we're actually making an attempt to respect the MPU. So yeah, jiggle things. Jiggle. You know, kind of one of the things we see is if we pause randomly, we're going to see that we're in an idle task on one core. Oh, we're still in an idle task on another core. Continue. Pause. Yeah, so spin lock. Port pending. Oh yeah, because, sorry, we're not constantly going to see ourselves stuck in I2C because we're interrupt driven. That's right. All right. So. And honestly, it's looking a lot more stable. So I'm gonna stop this, and then I'm gonna disconnect the debugger, and then I'm going to power cycle the RP2040, restart the UDP receiver, and so now we have our robot, and hopefully we'll start seeing data stream out of it. Yes, all right. So we'll just set it down, let it maybe calibrate, and then perfect. It's looking like it's kind of stabilized a little bit. And if I take it off its stand and let it freely hang about, I'll put it on my desk. I don't know if how tilted my desk is, because the thing is, it really looking like it's well, okay, it is kind of upset at me for powering it up the way that it did. All right, so because if we look at, all right, so it's looking a lot more stable than it was. We're running at 400 kilobits per second. We sped it back up, and 400 kilobits per second. We sped it back up, and now we're running wireless, and you know, as you can see, I mean, well, the little debugger's hanging out of it, but we're completely free, and it still hasn't crashed, which it almost certainly would have with the previous setup. So we haven't even implemented DMA yet. So, yeah. We're streaming. It looks like we may have fixed the MPU6050 problem we were having. We didn't even have to implement DMA. I mean, we probably should, but it is a bit of complexity. I did put the DMA in the title, so maybe we should just go ahead and do it. but I'm saying this like I don't actually know how to do it off the top of my head. I found a library that I hope works, you know. Yeah, so, well, if I can fidget with it that much and it not crash, it is probably fine. So, okay, let's plug the debugger back in. And we shall kill the okay, well, that can just keep running. Wow. It doesn't break. That's perfect. All right, so we'll just close all of this stuff. Disable pulls, do that, close that, use J2C, devlib, jruberg, close that. All right, so now let's just go in here and close. Okay, we'll stop listening and we can start listening again. Perfect, I love it. It is working so much better than it once did. All right, so let me commit the state that we're now in. And that is a long time for just a tiny little piece of code. So what we're going to do now is wait until interrupt has been triggered. Wait until IMU interrupt has been triggered. Wait until bytes in 5.0, or well, we don't actually have to wait anymore. All right. We should probably query the interrupt status more frequently, but we look like we're doing fine for now. We've created this counting semaphore with up to 1,000. We've done this, sped the bus back up. Added the interrupt. All right, cool. That was a long time just for this seemingly simple little piece of code. Either way, the whole point of this exercise is I don't actually know how to do this off the top of my head, so you are all following along with me. And we'll add the modified launch, because I think that's what was breaking. Git. Okay. Commit-m, actually, sorry, git reset VS Code /launch cat, git diff VS Code. We commented out the run to entry point stuff. Okay. Yeah, we'll just add it. VS Code, commit-m, move to interrupt-driven loop for MPU6050. Let me push that. All right, and let's see if it's still running. Look at that! It hasn't crashed. I think this interrupt code really did fix this. All right. Very cool. So, since I said I was going to try to get to it anyway, we're going to check out this Pico, this DMA-based I2C driver for the Pico. And so the reason that this is important, or interesting anyway, is so one of the things that I think we went over last time with the MPU code is if you look in I2C dev, basically the class that the MPU6050 driver uses to interface with the I2C controller on the Pico, it uses these blocking commands. So essentially, the Pico, or when the MPU6050 driver is asking for bytes off of the MPU, what actually ends up happening is it goes out, it starts the operation, and it doesn't return control back to the program until that transaction is completed. So the problem is, I mean, right now that's fine because like we're not doing anything else, and we have 2 cores, so one core could be sitting there doing IMU logic for all we care. The other one could be sitting there doing network logic for all we care. So that's honestly fine for now. But it is blocking the thread. So what we can do instead, one approach would be just to use an interrupt-driven model, or again, like we did with the MPU6050, using interrupts on the I2C controller. in the Pico, so that the CPU would only service the task when there was something to do, rather than just sitting there in a busy loop. But we could also take that one step further, because if you're used to the Arduino, where you kind of just it's up to you to query hardware, it's up to you to move data around. The Pico, being a much more modern, or a very modern SoC, or microcontroller SoC anyway, has what's called DMA, or direct memory access. And what you can set them up to do is, rather than, if you know that you need some blob of data to be fed into the controller, or into something, and there's not going to be, how do I describe this? If you know that there's some blob of data that needs to be moved, whether that's like memory to memory or memory to device, you can use something called DMA. And effectively what it is there's a separate controller that has access to the memory bus of the CPU, or of the SoC. And rather than a piece of hardware saying, I need attention, I need serviced, and then telling the CPU, sending the CPU an interrupt, the CPU waking up and having to service the device, DMA lets the CPU keep doing whatever it was doing, and the hardware, the peripheral, can just request from the DMA controller to send it the next byte, or the next piece of data, if it just needs to be reading some data. And so what that lets you do is the CPUs can just run off and do whatever they need to be doing. And if there's some simple task like just copying memory from some buffer into, say, an SPI controller, an I2C controller, you can let these DMA engines handle the copying for you, rather than having to spend CPU cycles. So by default, the Pico SDK, it's very much like the Arduino. It doesn't use many of the advanced features of the hardware. So I was just Googling around in the last stream, and I found this Pico I2C DMA project, and I have not tested. I have no idea if this works. But presumably it's based on DMA. And if you look inside of the implementation, notice there's a free RTOS kernel import. Inside the implementation here, it actually does, it actually uses free RTOS semaphores and stuff. So the cool thing here is that it is already RTOS friendly. We can just integrate, it'll sleep the thread when it's waiting on an I2C operation to complete. So I want to try and model, what do you call it? I would like to see if we can replace all of these blocking operations and replace it with these DMA versions. So so starting with that, let's see. Can we just add this example to? Does it do this as a library? Add examples source. CMake. And it just does. Okay. Source free RTOS kernel heap 4. Well, this might work. Might not. We'll see. Okay. It's very possible that it works. It's also very possible that it doesn't. So we're just going to git clone this. We're going to do a dependencies git submodule add, copy that and call that Pico I2C DMA, and then git submodule update init recursive, just to make sure if it has any deps we pull them, and it doesn't. So then in our CMake lists, we will then add a DMA I2C library, add subdirectory Pico I2C DMA. And we're going to add that before I2C devlib, because we're going to modify our I2C devlib. And so that ought to let us compile. And because we're building specifically, rather than building all, we're building just our configuration. So if we were to say depend on I2C DMA in our code, which we will say that we do. We'll just go into devlib here. We'll say I2C DMA. And if we build now, it should pull. Uh-oh, it's not working. Free RTOS. Okay. Well, we're going to have to write our own CMake list, because this is not going to work. That's sad. Okay. And it doesn't because we need to set up third-party GCC RTOS config. Okay. Oh, that's sad. Okay. Well, actually, so that what's happening here is we're adding our free RTOS config in source, which is fine. Well, actually, it's not fine. Sorry. So we're when we link to kernel heap 4 and we need a free RTOS configuration, that's coming from in here. Oh wow. Sorry. This thing needs free RTOS STK config, which needs Okay, I'm sorry. Go to the top level. Basically, one of the headers it's expecting to be global is not found. So what we need to do is, I really hate doing this, but we're gonna do add, we're gonna say include directories. I really hate doing this because it breaks isolation. But so if we do compile from here, now we have that free RTOS config header that we want. But I really don't know if... so we're looking at Pico SD source, CMake. How many copies of free RTOS did we end up with? Basically. Because I want... You know what? You know, Okay, what we could do is do a, as I don't know if, okay, you know, just for now, what we'll do, we will nuke our build directory, and then we're going to do a compile. Maybe this is fine. Maybe it's being okay. So let's just try this. So we're going to look at the interface of I2C DMA, and we are going to. So we've gone in. We've set up I2C and init. Actually, let's look at their example. Source. I2C DMA. We'll just look at the include. We'll look at the header. We're going to look at this bouncing ball. It's just something. Oh, that's complicated. Okay. Sorry. So we're going to look at. We don't need to call this anymore. We just do. What do? We just do that. We then do. All right. How are we going to integrate this? MPU. Does this actually touch the RTC hardware at all? Hopefully not. I don't think it does. I don't think the code in here actually touches the I2C controller. I2C. Sorry. I2C. It's a dev read bit. I2C 0. No, I2C 1. Okay, cool. I2C dev. Public. Static. Point lids. Okay. So actually, what we'll do is read byte, read byte. Divider, read byte, blocking ITC1. Okay, actually, what we shall do is, okay, so I guess we're also going to need a static, include I2C DMA.h. Oh, I didn't like that. Didn't like that. Because it does not. Because we're not linking with it. That's right. Okay. I thought we were. Wait. Let's see. Make no. Wow. Bad. Yeah, I2C DMA. Yeah, it'll probably be fine if we build. Oh, Pico Balancer is the one that's not appreciating it. Okay. Alright, private, that's why. Link libraries, I2C lib interface, I2C DMA. Okay. Compile. That did not work. It did not like that. What did I do? Where have I gone wrong? In function. Warning, error conversion. Conversion expected, unqualified ID. I did something wrong. Oh, that's why. I left that there. And still didn't build. And did something else wrong, presumably. Erroring conversion. Build command. Sub command failed. Failed I2C dev.cpp. Why did that fail? It failed to include I2C DMA.h. Which. Oh. Okay, just some fun CMake shenanigans. Interface means it only includes headers. It only includes that library for things that are linking to it. Public, it exports anything that depends on you will depend on that. Private is only things that don't leak dependencies at all. Okay, so we got that building. Cool. So what we're going to do is first we need to create a static I2C0 DMA, or I2C DMA, essentially. So I2C DMA T, I2C DMA. Why is that bad? Why is that bad? Why is that not working? End of what? Okay, static. No, we're fine. Cool. All right. And then we shall. So what we're gonna do here is CDMA in the main thread. We will pull up IGC init. Change that. In here, in our main task, initialize the I2C engine. Actually, we can actually do that in the IMU thread. Probably a bad thing, though. In case anything else ever wants to use I2C. So we're going to need to do auto RC equals I2C DMA init I2C1. Actually, sorry. I2C dev I2C DMA. Actually, it does this before. Oh, no, we're good. We can do this. We can do this before. Okay. Before we start the main task, we'll do. I2C DMA init 0 I2C 0. Because does this not have any? Pointer to a pointer. I2C instance. Does this not? Wait a second. That doesn't make any sense. Where's this? Does this actually hold its stuff? It's a pointer to a pointer. A pointer to a pointer. All right. That's sussing me out. How does this work? Does it use malloc or? Ah, I see. Static. All right, that's fine. Domain init, and then we're going to use the I2C1 instance, and then the baud rate is going to be 40,000 times 100,000, or times 1,000. Sorry. SDA pin CL pin. Cool. We'll just kill that. If not Pico, okay, we just sit in a freaking loop forever. Yeah. We can return from main. If RC not equal Pico, okay. Return RC. What is mprintf? Is that? Mprintf. What does that do? Is that like monitor printf? What is that? Mprintf. Was that declared? Oh, common. Oh, it's a locked printf, as in only one thing can print at a time, so you won't end up with stuff mixed together. Oh, I get it. That's cool. All right, we're cool with that. And then, all right, so presumably we're up on the. We don't need the pointer. All right, cool. So theoretically we can compile. Failed. Undefined reference to. Because I'm stupid. Okay. We need. We need the actual storage for the handle to the DMA I2C instance. All right, cool. And now we can compile. Yes. All right. So now that we have that, we now need to go to every place that we see I2C1 effectively and change this to something that changes to this DMA thing. All right, so we're going to do. All right, so how easy is this to migrate over? So let's start with the first instance of I2C1 that we see, which is this. So right blocking. So let's try this. So I2C DMA. All right, so we'll do. As we're in here, we can do I2C DMA, right? Yep. And then address dev adder. Then the right buffer is the red adder. The right buff length is 1. Right? Awesome. Non-stop. Okay. And no stop. Okay. Right. This does the read write. Okay. Okay. Right. Okay. So the way that this works is it does a mixture of address. So it does if you want to do a. So if you've ever written I2C code for sorry. If you've ever done any work with I2C, you know that a lot of devices use the EEPROM interface paradigm. So basically what you do is you start writing and you, because it's half duplex, you start in write mode, you write the address, and then you issue essentially a restart, and then you start reading the data that you wanted. So there's this notion of a repeated start, where all I2C transactions begin with a start. We'll call it a start event. You then write the address and the device address and whether you want to read or write, and then you can then either start reading or writing from that point. But if you want to set the address, the paradigm usually is start, write the device address, write the internal address that you want to read, issue a repeated start, and then start reading from it. And then after the repeated start, you send a read command, and then so the way that this library is written, if I recall, they do what's called, rather than have this, I'm going to write blocking with a flag set that says don't issue the stop cycle. So notice there's this no stop argument at the end of here. So if that's set to true, it basically doesn't stop the transaction. It lets you start another one. That issuing that repeated start. What they do here, or what this library does, is it does I'm trying to remember what it's called, a read write. Essentially, you do this write read, which you give it the device address, you give it the buffer you want to write, how much data to write, and then it'll do a restart and attempt to do the read. So what we actually want to do here is and it would return, what does it do? It does, if it returns Pico, okay. Count of bytes, red RC indicates failure. Okay, auto RC equals I2C DMA write read. Now we're gonna do the I2C DMA. We're gonna do the device address. We're going to do the register address, the write buffer length of 1. The read buffer is data, and then len. And then if RC not equals Pico OK, then we will return -1. And then we will return len, because we don't actually get... It doesn't actually. Basically, we don't know how much it actually did. It just does it. So we'll just do this. All right. Or not length. Length. Returns number of bytes read. Perfect. Number of bytes read. And or reads a block of bytes. Okay, perfect. And then we want to do a read words. Read write words. Oh, how do we do that? byte. Register to read from. Do we have... Actually, is there... Did this read... Oh, it's just okay. That's just the baseline. Right read. Pointer to address. Okay, so we can do. There is a read words I2C. So we'll do here is it actually it does this the way that we want. For datum. Data buffer length times 2. Oh, okay. So data buff. So this is doing big endian because the high byte is the lower byte. And okay. So all right. So wow. Okay. So we're trying to read multiple words from a 16-bit device register. We're trying to replace this function that reads words. Or 2-byte pairs, essentially. So we're looking through here, and the existing implementation does the same thing. We could do the same thing with the read-write. That would be a one-to-one replacement. But this does do... there is a read words in here, and significant byte is received over the wire first, which I believe is what we want. We can do a does this actually... Oh, wait. Read, write, word swapped. There is no length. Or is there read words, plural? Read, write, word, read byte, write byte, I2C read. Okay, so its word function does not support reading multiple words simultaneously. All right, so we'll just do the easy replacement then. All right, so count. Okay, we'll just return length. Count length. Ooh, length, number of words to read. Count is returns number of words read. Okay. Wait a second. Okay, sorry. Auto RC equals I2C DMA, write, read, I2C DMA, dev adder, reg adder, 1, rbuff is data buff, size of data buff. Okay, so then normally this would return the number of bytes read with a timeout, so count, but then it would return more than the data asked for, presumably. Length times 2. Will do. Size of data buff. And actually, it probably that size of probably isn't going to work because it's a dynamically sized thing. So length times 2. I think that's what it did. I think that's effectively what it did before. And then we can place this. The reward's red. I think it's just supposed to be length. If RC equals 0, or not equals, Pico OK, return -1. All right. Okay. Do that. And then the next one is I2C1. Write bytes, just fire it off. Ridge adder and then length. All right. All right, data buff is the register address. Oh, perfect. This works just fine. I2C auto RC equals I2C DMA. Write I2C DMA. Address is dev adder. Data buff. Length +1. If RC not equals Pico. Okay. Return -1. Let's return false. Return true. Or I should return. All right. Then write words. All right. So same thing. All right. Data buff and new len. New len. New buff. All right. So in theory, this is a replacement I2C1. All right, let's see if this works. It's entirely possible that it doesn't, but we'll see. It'll be fun. It will be fun and interesting regardless. Cortex debug. Firing it up. All right. Oop. Well, I don't see any data coming out of it. That's not good. Well, pause. There it is. It's working. Or something's working. I don't know if I believe it. So here, compile. Run. Yeah. It's creating those semaphores. Okay, how did this example do this before? I just don't know. All right. Let me run this without the debugger and then see if that makes a difference. We didn't have luck with starting up any free RTOS stuff before previously. Yeah, I don't see it happening. All right. So what we will do though is we will initialize the I2C up in the IMU task. We'll do that. The task delete null. All right. Compile and then debug. Hey, there we go. And we're reading. And if we go to Pico DMA examples, and well, you know what, let's trust our single stepping. Let's go in here. We're gonna try get FIFO bytes, and we're gonna go in here. And go over, we're gonna go in here, and go in here. Take me text time out. All right. Oh, damn. All right. I mean, yes, it worked. I just stepped over too much. All right. Over here, go in here. Go in here, go in here. All right. Commands restart, claim unused channel, TX channel is 2. Reading. Command bits. Set up the commands, claim unused channel. Perfect. So we'll just turn that off. Keep going. Nice. All right. That is definitely not the right orientation, but whatever, I guess. Okay. Yeah, something ain't right there. All right. And we'll just restart it, or yeah, we'll just start it up again with the debugger attached. And not talking as much as I did last time. I apologize for being tired. All right, so tilt, yaw. All right, tilt that way, and that one think it's. Probably mounted my IMU badly. All right, so that's working. We got DMA powered I2C. Perfect. So we are now. Oh, who left? Who came? All right. So we now have DMA powered I2C. We now have interrupt driven MPU reading. All right. So. And we've sped the queue back up to let's see, what's the MPU6050 max I2C speed? I think it's 400 kbits, right? 400 kilohertz. Yes. All right. So we'll stop that, and then just share this with it on the stand, just so we can see. Again, whoever's watching, feel free to stop me and ask questions, make comments. Just kind of muttering to myself if nobody gives me any topics. All right, so we have. It is good. All right, so I think now that we have the IMU working as we hoped, let's try adding starting motor control. Yeah, let's try adding the motors, and yeah, I think that'd be fun. All right, so I am using. All right, so motor control. So the way that this is set up is that there is an L298D motor driver, which is a quad half bridge set up as a dual H bridge, which lets us control two brushless motors. Two brushed motors, which are just these simple DC gear motors. I'll just hold it up to the camera here. So we've got these simple, just DC gear motors on the bottom that drive the balancing robot. So each motor takes 3 control pins, 2 directional pins, and 2 PWM pins. Essentially the directional pins are which direction each of the bridges is set to, each of the half bridges is set to. Basically positive or negative on each side, and then the PWM pin is the enable pin that effectively lets you control the speed of the motor. So these are attached to. Let's see which ones are which. Let me just power this down just so I can have no fear of shorting things out. All right. So, before we get into that, let me just commit the DMA-based code right now. Status, list, dependencies, and source, git commit to sem, migrate to DMA, I2C DMA to drive I2C. Actually, that's a terrible message. Let me amend that message. Git commit. Switch to a DMA. Integrate the I2C DMA Pico I2C DMA library for DMA for RTOS friendly I2C. Based on the RP2040's DMA channels. And let's do git push. All right. So, all right. Now that we've committed that, let's go back up here, and we're going to define motor 1A, motor 1B, motor 2A, motor 2B. And we'll just call it motor left, motor right. Define motor left PWM and motor right PWM. We'll just put these here. All right, and so for the left motor, that one is which pins are these? So the white ones are the PWM, the okay, the white ones are the PWM, motor left or motor right. PWM is, let's get the 6th GPIO up on this side. So 1, 2, ground, 1, 2, 3, 4. GP21 for motor right PWM. Motor right PWM is pin 21. And then the blue for, did I even do that right? Motor one, yeah. And then the blue for the A channel, well, AB, A channel, in 1, in 2. So the blue is A. So that is GP20, and then B is 19. And then motor left is then 18 for A, 17 for a B, and then 16 for the PWM. Yes, 16. All right. All right, cool. We got that. Oh shit. Got that. We shall put this back up. All right, cool. So we're now going to go look at one of the. We're going to go try to look at a PWM example. We'll close off these I2C. Although here, let me just make sure I give this repo a star. Cool. I already did. Perfect. Love it. All right. So, PWM. So let's start by deleting. Wow. Okay, hold on. Git, add, start, git, commit, amend. All right, cool. Perfect. So we're now going to do set up the PWM, set up the motor GPIOs and PWM. All right, so GPIO init, motor left A. We'll do all of these 1, 2, 3, 4, 5, 6. Left B, left PWM, right A, right B, right PWM. And then we shall do GPIO set dir, motor left A, GPIO out, GPIO set value, set high? No, GPIO set value. Huh. I can't remember what I actually turned on the GPIOs. GPIO on? No, GPIO something. Pull GPIO put. Okay, that's how I set things. GPIO put motor left A false. Or GPIO off. Low. No. False for low. All right. Cool. All right. There's probably a group. There's definitely a group way of turning these things on, but we'll just do them the easy way for now. Left A, left B, PWM, GPIO set function, left PWM, All right. We're going to do right. Right. A. B. All right. So we'll do the PWMs together. GPIO set function. Motor left PWM. Sorry, motor right PWM. GPIO PWM. All right. And we'll do void setup GPIO. Setup motors. All right, just because this is getting long. Just delete that. All right. And we're never going to want to do that again, so we'll just delete that for now. All right, so let it motors. All right, so we'll do hello PWM, hello PWM.c. We'll see. All right, 4 cycles, 0 to 3 inclusive. I don't actually need to do this. What does that actually do? Their input 0 set function. SIO. Oh. Okay. I'll actually have to do that then. All right. All right, so we shall do GPIO, or actually, we need a link to hardware PWM, so that'll be all right. All right. Close all this shit now. All right. Oh, compile. Perfect. Function. PWM set wrap. Nah, basically we're trying to set lead fade. How about that? Lead fade, PWM lead fade. That's right. Set divider uses class 6 systic. Because the basically what we need to do, let's look up I'm starting to trip over myself. Right. So the first thing that we need to figure out how to do, is set the frequency of the PW. First we need to decide how much. So using this wrap function, we need to decide. Sorry. Okay. So there's two things we need to worry about with the PWM. One is we need to figure out we need to figure what the frequency is, and then the second thing we need to do is figure out the wrap. So with that, basically the input to the timer that generates PWM by default is tied to the system clock, which in the case of the Pico by default I believe is 125 megahertz. So the problem is that the L29 you take that 125 megahertz and then you divide it by how many possible states the PWM counter can be in. So let's say we want an 8-bit counter. Basically, we want to be able to set a 0 between 0 and 255 for 256 possible output state or levels or output states or output frequency, output duty cycles. So because there's 256 states in an 8-bit counter, you would divide 125 megahertz by 256 and do some quick math. That's effective. That's basically 500 kilohertz thereabouts, or I mean 128 divided by 256 would be 500 kilohertz. But effectively, we're talking about around 500 kilohertz, and that's way too fast for the L298D motor driver. I'm trying to remember what the maximum frequency is. I think it's like something as low as 20 kilohertz. So I need let's double check the L298D's maximum drive frequency. Yeah, commutation frequency might be this 25 to 40 kilohertz. Source current turn on delay. Yeah. Okay. So we're gonna say 25 kilohertz. Thankfully, I mean it's bipolar, so it's faster. No, can't remember. All right, but we'll take the lower bound, 25 kilohertz. So we need to take our 125 megahertz signal, or SysTick signal, and we need to divide that by 25,000. So we want to wrap at 5,000. And basically at 125 megahertz, a count of 5,000, or 5,000 will overflow 25,000 times per second, or 25 kilohertz. So what we need to do, so we don't have to worry about setting this clock divider. We'll just do PWM set wrap. I need to include the, sorry. Include hardware PWM. All right, so PWM set to wrap. Slice number, actually. So that's GPIO to PWM slice, GPIO to slice number, motor left A. The wrap value, because these are 16-bit counters, so 5,000. All right, then PWM set enabled, slice number, PWM GPIO to slice num, motor left A. True. All right. And do that to the right one as well. All right, cool. Nice. So this now lets us control the motor, set the motor. So what we'll do is we'll do something just very basic right now. So okay, so we're gonna add two helper functions to set the PWM, or actually we'll just say, make sure to define this. Define motor wrap at 5,000. Motor PWM wrap. And we'll come back here, motor wrap, motor PWM wrap. All right. So to make this easier to so just to give ourselves a super simple example, we're going to add a couple of functions here that let us set the motor speed. So we're going to say void set motor speed. And we're basically going to accept negative to positive 5,000, 0 being stopped. So say so we're going to say int 16 speed, set motor left speed, void set motor right speed, int speed. All right. So we're just actually going to we're going to set these as these are going to be implementation. All right, so set up motors. So if speed greater than 0, then GPIO put motor left A true, GPIO put motor left B false. Basically, if A is true, B is false, it'll go forward. B is true, A is false, it'll go backwards. And then PWM set value, or set how do I actually set the value? Counter, right? No. Yes? No. Set, clear, what? Going up, moving up, init. PWM set chan level. Set chan level GPIO. Alright, set GPIO level. Motor left PWM. Speed. Alright, else if speed less than 0. Going to do the other one. False. True, and then negative speed. Else, I'll set them both to false, which will make the motor stop. All right, we're just going to copy and paste this for the other motor. Right. I'm going to say if speed greater than 5,000, speed equals 5,000, else if speed less than 5,000, speed equals negative. We're just to clamp the input values. All right, cool. And this still compiles, right? Cool, yes. And just to make this super simple to control, or just to give a super simple control for this, we're actually gonna start writing our balancer loop. It's gonna be kind of crap right now, but what we'll do is set motors according to tilt. So we're going to say, max speed or tilt limit is equal to 5 degrees. And so basically at 5 degrees, we want the motors to go as fast as they can. And so what we'll do is we'll call it, tilt limit 5. And then if, and so what we'll do is, float response equals tilt equals orientation dot tilt or pitch time or divided by tilt limit tilt limit times float times float motor PWM wrap. All right, so at 5 degrees, it'll 5 divided by 5 is 0, or 5 divided by 5 is 1 times the wrap will be 5,000. And so we'll set left motor speed to response to response, and set motor right speed int 16_t response. Perfect. All right. So this is effectively what's called a proportional controller, which means that at our tilt limit, basically this is you can imagine that this would be 1 point. So tilt limit 5, we're going to convert this in just a second. So I also think, I can't remember if I wired these up the right way. Either way, okay. So we will compile this, and then we will run this. Well, before we even do that, let me put in the batteries. So negative goes that way. I haven't powered up the motors in this thing in ages. That goes that way, and the positive goes this way. All right, fully powered. All right, deploy the code. Well, it's doing something. 296. Oh, perfect. Well, it's setting something, but now the motors aren't turning. Motors aren't turning. Why are they not turning? Didn't blow up my regulator, did I? Not turning. Why are they not turning? No, I wired that correctly. Negative, positive. Alright. Well, alright. Something's funky. Why is that not working? Why is that not working? Alright. Why is that not working? Why are you not working? Alright. Yeah, we're gonna have to subtract some. Okay. Something's not right. Motor left level. There you go. PWM level associated with a GPIO. Well, something ain't working. What ain't working? Is it motor? Well, that's also incorrect. I don't think that's what was wrong though. Okay. Why? One. Alright. That. Oh. Why are you not working? Oh. Aye. Interesting. So the call is being made, but the motor setup is not working. Put motor left, B, right. Set function. Oh. Well, that'll explain a lot of things. We configured the PWM incorrectly. Look at that. Look at that. If anybody saw that earlier, congratulations. But that looks to be what our problem is. Shall run. Now let's see if the wheels start spinning. Pretty please. Hey! The wheels are spinning. Although they immediately go full speed, regardless of what you do. So I also need to I think the right motor needs to be reversed. So, I think the left motor needs to be reversed. So we'll do false, true, true, false. All right. So yeah, just so you can see what's happening right now, let me pick this up. Basically, it's if I tilt the robot one way, the motors turn. If I tilt it the other way, they go the other way. But there's absolutely no throttle control. It's just jerking. I don't know why yet. So we got to figure that out. All right, cool. Pulled the battery. All right. So why are the motors not throttling? So if we put a breakpoint there or a breakpoint here. Oh, we're not debugging. That would help. That would help. Oh, wait a minute. Why is it coming in at 5,000? Oh. Again, negative 5,000. Okay. Wow. I failed at that. Alright. Okay. Alright. I failed at that. It's getting... That's what happens when you program when you're tired. Alright. Perfect. And we're just gonna hack in an offset right here for 3 degrees because I think that's just the IMU mounting. I think that's just the there minus 2.8. Okay, cool. This is actually doing what I hoped it would. All right. So we're gonna power this down here. Well, we're gonna unplug the debugger, and we're gonna just tie off this cable here. Hopefully. All right. I'm gonna restart this outside of debugging mode. Let this power up. All right. Get this lined up. All right. All right. So we've now programmed it such that if it falls one way, it speeds up. If it falls the other way, it tries to counteract. And so as we rotate the robot through 0, the wheels stop. In reverse direction and speed up depending on which way it goes. So if we try to okay, I gotta grab the camera. I gotta grab the camera. Okay, that was just too cool. Alright, let me power up Droid Cam on my phone. And switch back to my dashboard here. Droid Cam. Verify. Alright, here, hold on. Droid Cam. Let me switch to my desk cam here. Try to turn on the camera. All right. Here, hold on. So let me switch back to this. Sorry. Grab the robot first. All right. It's hard to do. Okay, this is really hard to do one-handed. Alright, desk cam. Alright. Just trying to balance. There we go. There we go. We have a balancing. It does. The balancing algorithm's pretty bad, but it tries to balance. It is attempting to balance. But we need to make our PID controller better. Or, well, we need to implement a PID controller. Oops, sorry. Alrighty. So it's working. in some capacity anyway. All right. So, that was really successful. Okay, so, other than the fact that it's not quite good yet, so what we need to do now is actually implement a PID controller. I guess that would work. Make it spin in a circle of the centripetal force. Keep it upright. Like that would work. I mean, that would be a thing, but wouldn't be quite what we're after. So now we need to set up what is called a PID controller, a proportional integral derivative controller. Basically, when the robot is just purely reacting to when the robot is just purely reacting to an input error, it'll always be slightly wrong. So what we need is essentially damping factors to adjust for inherent steady state disability. Wow, I'm doing a horrible job of explaining PID controls. Did not sleep well last night. Okay. So PID stands for proportional integral derivative. The idea is that a response from it is a control algorithm, and the idea is that the response is a mixture of a immediate response to the measured error, a response to the accumulated error, and a response to the change in error. And the reason that's important is so the proportional component, the immediate reaction proportional to the error, is essentially your quickly responding action. Like if it immediately starts having a problem, that is a response based on the measured error. The integral component, the response based on the accumulated error, is meant to discover steady state, what is called steady state error in the system. Being like, let's say you're trying to drive at a certain speed. The integral component would essentially hold your value of, or would essentially, or sorry, let's say that, say we're trying to hold a velocity, and basically the input value, if you had zero error, essentially you were at the correct speed, there'd be zero response from the proportional, there would be zero response from the derivative component because the error would be zero. But the only way that your motor could actually be turning at that velocity would be to have accumulated steady state value in the integral component. So with this balancing robot, the steady state error would be the IMU not being quite mounted right. I mean, remember, or just if you were paying attention, I didn't really say it too much, but this orientation minus 2.8, I measured that when my robot's sitting on the table, we can see that the IMU is measuring 3.1 degrees, even though it's supposedly level on the table. So I just subtracted 2.8. What's button doing? Hey, button. What are you doing? Come here. Sorry, my cat tax. And then, sorry. So where was I? So yeah. So I've subtracted this 2.8 degrees from the IMU because it's not mounted quite level. But the integral component of the measurement would learn this, or would end up learning this. So we are going to migrate to a PID controller. So let's rewrite. So PID. So okay. So let's rewrite this. We call it. Let's see. Const float. Or sorry. So PID output would be. It would look like response is equal to a proportional constant times times the error plus a derivative times the sum total error plus KD times previous error minus error. All right. So what we're going to do is we're going to delete the ki component for right now. We're just going to look at the damping factor. So right now our p is essentially our p value, or sorry. So we're going to say so we're going to start with defining our error is equal to our orientation dot pitch minus 2.8. I will just say dot 3.0. So this is the input error to the system. Input error. And we're going to say float previous error equals nan, or not a number. We could say if previous error equals nan, then previous error equals error. All right. So then we're going to float some error equals 0.f. All right. Shall I'm not going to worry about some error right now. So we're going to say float. So in this case, our divided by tilt limit divided by 5, we could say that our kp is equal to 1 over 5. Basically, if you divide by 5, that's like multiplying by the reciprocal or multiplying by 1 over 5. So we're going to say const float kp equals 1.f over 5.f. Let's say const float ki equals, we'll just say 0 for now. Const float kd equals, just say 1.f. It's probably bad. Okay, so then we're going to say error under the curve. So we're going to say sum error plus equals error. Say ki plus times some error. We have to be really careful about the integral on here because if things just sitting on the table, it'll spin up. So we're just gonna say response, and then this whole thing is going to be response times equal float motor PWM wrap. All right. So, all right. Previous error minus error, some error. Sorry, error minus previous error. Is there a benefit from defining the constant loop? Absolutely not. There's absolutely no freaking benefit to that. Just quick and easy. Realistically, I want them to be adjustable, which is why I went through the effort of creating this whole network interface thing. Was the idea is that there's going to be a we're going to build a little visualization dashboard that we can control the constants from. But I'm lazy right now, and I just want to see this work. So we're going to do it by hand. So we're going to say, we're going to make that 100, the damping factor. Response times EI plus. Okay. Perfect. So we're going to do that. So ki is 0, so that won't contribute. So we're just going to be a PD controller, essentially. So compile. And run. Plug the debugger back in, and we'll deploy the code. running. And we're running. And we're not doing anything. An error. Let's pitch some errors. 45. Response is optimized out. Uh-oh. Uh-oh. Response. Why is it not? Okay, well, that's funny. Alright, we'll just, put it here, response. Why is this being this way? Alright. Motors are no longer running. Compile. Deploy. Infinity. Oh dear. Ah! I see. This never worked, because... Ah! You're right. Alright. There we go. That's it. But also... Alright, let's see. Oh, Jesus Christ. Okay. Oh, God. What's that? Is 10? Oh, God. Okay. Alright, let's try that. Let's see what happens. Alright. Ah, that's bad. That's not quite working. I could show... I would show that to you, but, yeah, there's no way I can hang on to it and the camera at the same time. You know what? Hold on. Let me grab my, grab my little tripod thing. let's adjust the thing. So we're gonna change this to 1 or 5 times the proportional. Power that down, disconnect the debugger, which I just freaked the hell out. All right. Oh, not there. Power this back up. Let that start up. And let me change this over to the desk cam. Let's attempt to see what happens here. It's more or less working. Doesn't want to stop moving, but let's try it on the floor. Oh God! Okay. Okay. Right. Alright. So and then accelerates off in a direction. That might be why the I value is needed. All right. So, okay, little booger. Okay. Yeah, pretty much. It's we're gonna add a 0.01 Ki value. Start with this as 0.1. Let's try 0.25, 0.025. All right. So, really? Oh, nice. Okay. Run. No. Go Flash project with the SWD debugger. All right. Cool. Well, I don't know if I trust that this is going to work, but we're going to try. I might have to make this a much smaller value. Just try this here. Let's see what this does. Oh, heck yeah. That seems to be generally working. Although it doesn't speed very well. That might be too much integral response. And this is why we use a web dashboard to control the constants, so we don't have to keep doing this. Oh, well. And now tape a knife on it. Yeah, we could do that. Stab everybody here. All right. I'm trying to think whether this means that I have too much or too little KP. Yeah. Thinking that I might have too much, so if we basically 001 would be, let's try KP divided by 100. What if we used a smaller damping factor? Like, what if we did KP divided by like 1,000? Just gonna throw random numbers out there, see what happens. See if it gets better. And we will compile, and we will deploy with the SWD debugger. New party game, don't get stabbed by a knife segue. Yeah, pretty much. Oh, well, yeah, it would help if I'd actually plug the power back into it. Okay. Flash. There we go. Used by task so close. Let's see. Oh, I do need to start it up on the stand though, otherwise it'll freak the hell out. That's less than ideal. All right. All right, that ain't working. That ain't working. That's a lot worse. Nope. That was a lot worse. Now we're going to go back to our previous constants. We'll keep KD, but we'll... Alright, so we're just gonna try lowering the KI. Alright, so Flash project. I need to compile it first, right? No work to do. Good. Terminal. Alright. Alright. Alright, it's worse, kinda. Well. Uh-oh. Oh dear, it's totally flipping. Ah! Oh, okay. So, what have we learned? We've learned that I can't wing PID constants. Alright, okay. So... plug this back in. Oh, shoot. Alright, I think the earlier constants were better, you know, like 0.01 half. Alright, so maybe we need to increase the D response too. Alright, so we're going to compile that, and we're going to flash the project. that made it a lot worse. I think we actually need to decrease the KD. We'll probably pull this down to 0.5. And then compile. And then flash project. Oh, wait, we're not plugged in. Flash project. Yeah, 0.025 was definitely least aggressive, was less aggressive. Okay. Ooh. That's working real good. Okay, hold on. Let me switch to the desk cam. Let me wake up my phone. Switch to the desk cam. There we go. I'll put this on the floor. Yeah, the other thing too is that it's not actually trying to like go in any particular direction. It's basically trying to get it to stand still, but it doesn't actually know when it's standing still, really. Other than, so it's probably going to need to mix in the encoders so it knows where it is. All right. Okie dokie. Desktop. Unplug the power. Put it back on its stand. And change the camera thing. Alrighty. Let's see. Hold on, what was bleep bloop? Okay. So, as Danish 42 said, I should probably, I think this might have been working better with 0.25. We might also want to, we'll try with 0.25 and still KD backed off. Well, just to re-experiment. Just so we remember what it looked like, we'll compile that, and then we shall reconnect power, do this. The amount of time that I have spent plugging and unplugging it, I wonder how long it would have taken me to actually learn. You know, okay. You know what? After this, we will, what time is it, 10, 12? Oh, jeez. Okay, I gotta end this in 15 minutes. Because I gotta get up early tomorrow. Alright, so program in these new constants. And then All right. Where's the Python script? Oh, good Lord. All right, so unplug this. We're gonna reboot the computer, or sorry, reboot the microcontroller. All right. Just can this. This off the stand. There we go. It's standing pretty freaking still. It's standing pretty freaking still if we push it in a direction. All right. Just to play with this, we shall, what we shall do is, so we're gonna save where it is right now. We're gonna commit this. All right, so new terminal. Oh, sorry, desktop. All right, so. We're gonna add source git commit -m. It freaking balances. All right. So I am gonna decrease the KD response to 0.5 and see if that does anything interesting. No compile. A flash with SWD. Oh, it's not plugged in. Of course, it's not plugged in. Yeah, it's not going to work. All right. All right. Horrifically wrong. I think that's just the MPU being funky. Hold on. Let me just dock that again. All right. All right. All right. Desk cam. Let's see if this Clearly we need more damping response. All right. I think it is probably high time. Well, actually, what is it? 1018? All right. One more. So, let's try 1.5. See what that does. Compile. And we'll check out how this works, and then in the next stream, we will build our PID visualization dashboard and see if we can tune this. All right. Oops. All right. Yeah, I need to flip it to the portable camera. All right. Now it's like too damped. Okay. Well. All right. One more time. All right. Well, we shall revert to about 1.1 or 1.1 pile. 10% more damping. All right. Cam. Huh. Interesting. Okay. Well, I think that is probably enough for tonight. we've got it pretty much balancing. There's some errors, but it's looking like it's working pretty good. Or, well, all things considered. All right. Okay. So, we have a robot that balances. Doesn't do anything other than balance, somewhat. All right. So, in the next video, we're going to basically add logic for it to move around, or an attempt to actually control where it is. So we'll start by trying to have it hold position. So that means the next video is going to be adding the encoders. Implementing support for the encoders that we already have. Let's see. And then, basically adding a PID controller on top, a second order PID controller on top of that, to control the position. And all right. So, but that means in this video we accomplished making the MPU not crash. The robot crashes into things, but the software does not crash. The MPU does not crash. We implemented interrupt-driven support for it, which works. We've implemented a DMA-based I2C controller, or I2C driver. So we now are RTOS. It's RTOS friendly, I2C. And we have our PW motor control, and it sort of balances, or it seems to balance, but it likes to run off in directions. So our goal is that we're going to try to get it a little less jittery in the future, but more or less, I like or the fact that it can stand up on its own. It just needs a little bit of tuning. But yeah, so that's where we got to. And yeah, so in the next one, we'll add support for the quadrature encoders via the Pico's PIO blocks, and we'll add the second order PID controller to control the position. And someday, maybe we'll do visualization, or maybe I should do the next segment just on the visualization, so we finally actually do it. Maybe I do make the next section the visualization. Either way, so I guess join me again next week on more balancer robot stuff. And if you haven't check out the Bare Metal 386 series. I'm still trying to get a video. I think I figured out how to get through the bug the logical problem I've been having with the emulator. I think I figured it out. But either way, see ya. Thank you so much for watching, and see y'all next week. Hopefully, or I'll be back on next week. Y'all can come back if you want. Thanks for watching.